So far, we've basically focused on looking at explicit solutions, thinking about eigenvalues, etc. What I'm going to do now is develop a geometric way to understand what's going on here. And that involves just going back to what exactly we mean when we write this x prime equals ax down. So I'm going to go ahead and think of this as x and y. Those will be scalar functions. Their derivatives are given by this formula, right? So a times x plus by is x prime, and c times x plus dy is y prime. And I want to think back to Math 114 and say, what kind of a thing is this right-hand side? Well, it depends on x and y, and it spits out a vector. So what do you call something that takes in two numbers in the plane and spits you out a vector in the plane? That's a vector field in the plane. Back in Math 114, we might have written this something like that. What does this vector field have to do with solving the differential equation? In order to understand that, let's just plot a bunch of different vector fields and solve the equations and see what we get.
Let's take a look and see what thinking of our differential equation as a vector field does for us. We'll start with a pretty basic one, this equation number 1 here, where the coefficient matrix is 1, 0, 0, 3. That means we're going to have 1 times x plus 0 times y. I've traditionally called these things x1 and x2, but you just think of them as x and y like we normally do. And y prime is going to be 0x plus 3 times y. And you go down here and click this button, Graph Phase Plane. And there you go. You see we've drawn a picture of this vector field like you might have done in Math 114. And the nice thing about this particular tool is if you click any point, like this point here, it plots the trajectory through that point. So this place where the cursor is x0, right? The initial position, and then you solve the differential equation and you get a curve. So let's take a look here, plot several different trajectories, and you can see they behave like we expected. Let's take a look at the eigenvalues and the eigenvectors and see what that tells us. So we have two eigenvalues, 1 and 3. They're both positive. They're both real. The eigenvector for eigenvalue 1 is 1, 0. 1, 0, of course, is along the x-axis. So if you click there, you can see I basically stay along the x-axis. And which direction do I move? In the direction of these arrows, so out. That's because both of these eigenvalues are positive. If you click on the y-axis, that's the direction v2. Again, you stay on that axis, you keep going up. Now, what you can tell from looking at this picture is that, in general, the curves tend to bend up. They're becoming more and more vertical. If you go below the axis, they become more and more vertical in the other direction. That's because the eigenvalue corresponding to v2, this direction v2, is bigger than the eigenvalue lambda 1, which corresponds to the horizontal direction. This is the vector field corresponding to matrix 2, 2, 1, 0, 2. You may recognize, looking at that that's the defective case. So we have one eigenvalue of algebraic multiplicity 2, but geometric multiplicity 1. So if you find the generalized eigenvector corresponding to that, it happens to be 1, 1. And then you apply a minus 2i to that, you get 1, 0. Let's see how that plays out in terms of graphing solutions or plotting trajectories. All right, let's plot a few and kind of see what's going on with them. So what's going on here is these curves all tend to flatten out. They tend to go horizontal. That's because our eigenvector is 1, 0. If we were to pick something right along this line, it stays along that line. If you start below that line, you're going to bend around and face backwards in the negative direction. If you start above the line, you're going to twist around and end up going to the right. And these are both positive eigenvalues, so everything moves away from the origin. Here is the vector field corresponding to matrix 3. It has one eigenvalue. That eigenvalue has algebraic multiplicity 2 and geometric multiplicity 2, which means that A is just a multiple of the identity. If you think about this in terms of the matrix exponential, it's very easy to compute the matrix exponential of a diagonal matrix. E to the minus 1/2 t times the identity. And that's what happens with our solutions. They all come, in this case, straight in because the eigenvalues are negative. Here's the vector field corresponding to matrix A. You can see it has eigenvalues that are plus and minus I, so they're purely imaginary. And the eigenvectors then have to be also complex. It's hard to make sense of what those look like visually, But if we look at this vector field, we can at least see what the trajectories of the differential equation are doing, and you can see they are making circles. Notice we're rotating clockwise in this example. This is the vector field corresponding to matrix number 5. You can see it has two complex eigenvalues with non-zero real part and non-zero imaginary part. Of course, they have to be complex conjugates. The corresponding eigenvectors are also complex conjugates. Let's go ahead and plot the trajectories. Well, you can see what they're doing. They're spiraling out. Why is it out? It's because this real part, 1/2, is positive, which means you have an e to the 1/2 t multiplied by everybody. Comes out in front like that. Now finally, let's see if we can figure out what happens to our zebras and our lions. Our coefficient matrix in that case was 0.05, -3, 2, and -0.1. We've plotted the vector field here, and let's pick a few trajectories. So what's going on here? You can see that generally speaking, we're going to spiral, and the question is which way. It's not so obvious looking at the arrows, but it is clear that we're following in a counterclockwise direction. So if you follow one of these trajectories around, you see that as you move counterclockwise, it comes in. So what's going on here? We are spiraling around. The computer has to stop at some point. The computations get too intense. But if you come close to the origin, you can see what's going to happen. You're going to spiral on into the origin. What does that mean about the zebras and the lions? It means no matter where you start, both these species are doomed. They are going to tend to the population 0, 0. What if we were to artificially enhance the zebra reproductive rate? Instead of reproducing at 0.05 or 5% per year, what if the zebra reproduced at 50% per year? The only thing that does is change its coefficient from 0.05 to 0.5. Let's see what happens. Now you can see both populations are going to get larger and larger. We're spiraling, in that case, out of control. So can we figure out what's happening here? It's exactly the question of whether or not the real part of the complex eigenvalue that we get from this system is positive or negative. So if we want to have a stable system, what should we better do? We should find the zebra reproductive rate that makes the real part of both complex eigenvalues 0.